just get it out of the way. Okay, we'll get started. My name's Tom Legata. I'm here representing Myrtle. Myrtle is a small AI ML company in Cambridge, England, full of a lot of really smart guys out of the University of Cambridge who are expert in various neural networks and all sorts of AI ML technology and how to apply it to FPGA to solve all sorts of various workloads. They couldn't travel, COVID restrictions, so you're stuck with me. I'm not one of the really smart guys from Myrtle, but I'll do the best I can to keep up with you, and we'll go from there. Okay, so effectively, and what I'm going to talk a little bit about today is this is something called SEAL. It's a sparse link accelerator. The guys at Myrtle really believe that hardware, software, co-design solutions at specific workloads are really going to give you your highest performance out there versus a hard-coded solution. And this was a SEAL sparse links calculator targeted specifically at recommendation. We'll talk a little bit about what recommendation is. But what it does is it actually accelerates recommendation challenges around memory and compute-bound issues. And we'll talk a little bit about what those are. It's an M.2 cartridge, and it sits right in the actual carrier, and we'll talk a little bit more about what that is as well. So recommendation models are really the most common of sort of the data center workloads. If you look at it, you know, somewhere around 80% of all of the AI cycles in the data centers, hyperscale data centers, are dedicated to recommendation. And recommendations used for everything from search to adverts to feeds, entertainment. And so accelerating recommendation is actually a pretty good thing to do. If you're not familiar with MLPerf is an industry standard organization. They created DLRM, which is a benchmark to gauge the performance of these recommendation engines, these recommendation models. Recommendation models are a little bit different from your standard workloads because they're comprised of embedded table lookups in which sparse vectors are multiplied by dense matrices over and over again in order to get, you know, various solutions out of this thing. And that's what's shown in that center. The sparse vectors are fairly random in nature. They don't lend themselves well to caching. And so what tends to happen when GPUs and CPUs run these workloads is they tend to get memory bound pretty quickly. And that's important because, you know, these memory bound operations really take up to about 80% of the runtime. And so if you can really accelerate these memory bound operations, then you can actually, you know, get some serious performance advantages on this thing. So this is what we did. I'm going to show you some benchmark results. That's SEAL. That's this. Anybody wants to see it afterwards, you can see it. I'll hang around. That sits in the Glacier Point carriers. Up to 9 of those will sit in that carrier and still sit within the TDP envelope defined by OCP. The Glacier Points go into the Yosemite cartridges, and the cartridges go into the V2.5 chassis. And as you can see, you know, these SEALs will stay within that 14.85 watt TDP defined by OCP, and they come in either 16 or 32 gigabyte of memory. And then there's programmable silicon in there. In this particular case, it's a Xilinx FPGA that's programmable. That enables us to actually adjust and tweak for new workloads, new operations as we go forward. Now, the reason that we've done this is that, and the reason we believe FPGAs for workloads and targeting them at workloads is that, you know, when these data centers go up, CPU motherboards go into data centers, there's an expectation of 3 to 5 years worth of life cycle. These workloads are going to change over time. And somewhere around mid-cycle, the workloads are going to have changed enough that a hard-coded accelerator is not going to accelerate as efficiently as it did at the beginning. Microsoft's well published on this. They like FPGAs for their workloads in Azure. And the reason we've used this hardware-software co-designed activity is so that in mid-cycle, as the workload is evolving, we can reprogram the device, retune it, and actually stick with the workload and get you that 3 to 5 year cycle. So I'm going to show you some benchmark results. This is the first benchmark that we ran. What we did is we took one of the Glacier Point carriers and we put anywhere from 1 to 9 of these SEAL accelerators in it, and one Xeon Twin Lakes from Intel motherboard in there. So half of that Yosemite chassis was populated. and we ran the models. Now, if you run this thing with 2 glacier points, 9 seals, 32 gig per seal, you can literally add up to over half a terabyte of memory to the system. And each one of these glacier point cartridges will add about 162 gigabytes of bandwidth, theoretical maximum for the system. And so the first benchmark we ran, I'm watching my time being very good for you. The first benchmark we ran was specifically around bandwidth addition. And as you can see, you got near perfect linear scaling as you add these in for bandwidth addition. We ran it across all sorts of bit depths. We ran it across a variety of batch sizes and between 8 and 64 of these embedding tables per lookup. And we got to nearly 155 gigabyte per second additive bandwidth, which is pretty close to that 162 theoretical maximum that we were talking about with 9 of these cartridges actually in there. The next benchmark that we ran was really a load gen traffic generator, okay? And that's what the load gen does is it gives you a specific latency bound. We were running with 10 millisecond latency bounds on this thing. And what we saw was that for full precision, single precision, float 32, you were pretty much linear up until about 8 cartridges, and then it started to roll over at 8 cartridges. And for half precision, the float 16, it was pretty linear up to about 6 cartridges. But what you can see is there's about a 4.5 times improvement over a CPU baseline for a single precision machine, and there's about a 6.5 times improvement over a CPU baseline for a half precision float 16 machine. So as you add these things, as you add these cartridges in, you continue to improve your compute capacity. And I'll give you one last quick benchmark on this thing, and this is actually contained in this data sheet if anybody wants it. I've got some extra ones over here. What we did was we took the Yosemite chassis down below. We took 2 glacier point carriers and we put 7 of these cartridges in each of them. And then we put 2 Intel Twin Lakes motherboards in there as well. And we ran a series of benchmarks. And then we actually took 2 of those Yosemite cartridges and we put 8 motherboards out there, and we ran 8 motherboards with the same set of benchmarks. And what we found is that we got anywhere from 5 to 8 times the performance with this configuration versus 8 motherboards. And that led us to, look at 41% of the power consumed, half the volume, half the cost. For 100,000 server installation, you're looking at about a $250 million savings for CapEx alone, and about $100 million in OpEx just on electricity, not including the savings in volume, where you only need 1 of those Yosemites versus 2 for the same workload with all CPU. So, we kind of look at this as, half the volume, half the power, half the cost, 5 to 8 times performance. These targeted accelerators actually tend to do really good for specific workloads. And so wanted to present that today. Anybody wants to see it, anybody wants to take a look at the data sheet, I have it over here. So.